something. I don't know. Yeah, and this recording, I'm gonna send it to she freaked me out. I never heard recording in progress. Yeah, and then probably if you missed something, you wanna watch it again. I don't know. You tell me how it would go, because when we were covering 5.1, it was somehow slow, and 1 hour may not be enough. So probably this way we can do it really fast.
Yeah, sure.
Okay, we can try. So describing fields, this is topic 10.1 in my book. And I assume it's the same with yours. Let me show you the book just to be on the safe side. Okay, what happens? Okay, it's here.
Yes.
Yeah, so 10 requires 10.1 and 10.2. So we're talking about the same thing. All right, so what do we have in here? I have planet Earth and the moon, and you can see the gravitational field. This is very similar to the electric field, and I know for a fact that you know a bit about electric field. It's as if I have two sources of field of the same charge. And you know, mass cannot be negative. So both have a positive mass, and the gravitational field acts exactly like the electric field. However, they attract in a way, so there's some similarities and some differences, right?
Okay, but if you said it's positive, then shouldn't they repel, no?
Yeah, so this is something that is different with the gravitational field. The interesting fact, so what's different is that mass cannot be negative. Another difference could be, how come two positive masses do attract? So this is also a difference. So we don't have a repulsive field, gravitational field ever. All right. I'm not worried.
Okay.
Yeah, it's never repulsive. It's always attractive. I'm not worried a lot about you understanding gravity, because you've been dealing with gravity since the day you were born. So you have more experience than any other alien coming from any other universe, you know? I'm interested in this region. Let me show you. This region where you have no gravitational field at all. And it should make sense to you, because you would be attracted to planet Earth and attracted to the moon with the same exact force, and eventually the forces would cancel out. Or let's not mention force, let's mention a point, a mathematical point in space where you have a field and another field equal and opposite, they cancel out. So in this region, probably you have no field. And the map of the field would show you that in this region it's practically empty, you know? All right, so what's the outline? You're gonna cover 1, 2, 3 gravity, 4, 5, 6, 7 electricity. So this topic is about fields in general. So it's gonna deal with electric field and gravitational field. And you know a bit of the electric field and know a bit about the gravitational field. I took those equations from the booklet, the physics booklet, to keep them as reference, because I want you to understand what they are. And I want to eventually probably add to them some stuff if needed, okay? Gravitational field, what you know, the definition, our starting point is that a massive body, so any body of mass m, it could be you, Rida, it could be me, we're not so massive though, we produce a gravitational field around us. Like me, everything is attracted to me, but the field is so small, nobody would feel it. If I would grow to be a planet Earth, everybody would feel it, you know? Like this pencil will fall down on me, not on Earth. Imagine.
Wait, what do you mean on you, not on us?
Yeah, so I have a very small mass. So the gravitational field I create is very, very small. If I would eat a lot and I would gain mass and mass and mass, I would be so massive than planet Earth, everything would be attracted to me, even this pencil.
It's you or to the Earth? That's not the confused. What do you mean?
Okay, who's more massive, me or the Earth? Let's imagine I'm more massive than the Earth. Yes, it's gonna be attracted to me, but I'm not massive than Earth. I'm trying to tell you, even if I'm tiny as a human, there's a field. To find the gravitational field G, you do G, big M, M is
this I know.
You know this one. All right, so you know it from before probably. And the gravitational constant is 10 to the negative 11. This is what makes the field very small if the mass is very small. So happily, and this is good news, nobody will be attracted to you. Otherwise, you're gonna move people out of you, and dust and pencils and stuff. All right, now if you look at the source, it could be a tiny planet or anything you want. The gravitational field is radial like the electric field. However, it's always inward. So it acts like a negative.
So what?
It's always inward.
Yeah.
Okay.
Is it attractive?
Yeah, if you want to call it attractive, why not? However, for me, a field does not describe the force. But since the mass is positive, field and force will always be the same. So talking about attractive, it has to be inward, it has to be talking about the force. Anyway, since you know that electric field could be outward and could be inward, I'm trying to say that gravitational field is always inward only.
But it doesn't mean it's negative, right?
No, the mass is positive.
Because we said before that electric field, like when it's inward, it's negative.
Yeah,
right?
exactly. So if I have a negative charge, the electric field is inward. It's as if the mass acts like a negative charge, if you want.
But it's not really.
Yeah, so it's a bit different. So gravitational field does not act like an electric field. This is the main difference, okay? However, you shouldn't be confused. Just remember your early years, throwing pasta on the floor and your mom going crazy. And you would know that it's always inward. This is what you know when you were a kid. You would think that planet Earth is flat, and you would think that the gravity is downward, okay? This is a simplistic view. However, Earth is not flat, it's a big sphere, and this is a zoomed out view, okay? So this is zoomed in and this is zoomed out. All right, so now you know how to calculate the field. If I move a bit here, I need to talk about the potential energy. So item 1 was only the field, and the field would be called small g. Now for potential energy, I'm gonna call it, I don't know, what do they call it? So far they call it potential energy. If I go to the equation, they call it EP. And you know potential energy back from topic 2. So I'm gonna try
MGH.
Exactly. You see this boy going up the stairs, and you would say that the potential energy is MGH, right? And you will take the reference for height. You will take 0 height to be this level, right? And as you move up the stairs, you gain potential energy. And potential energy has a unit of joules. This is also potential energy. You see a ball with low potential energy, a ball with high potential energy, and this is in between. It's related to the height. Okay? Now for planets, we're gonna take 0 to be at infinity, not at the ground. And this is gonna shift the way you see potential energy tremendously. Okay? So when you are at the surface of Earth, it's gonna be negative. And as you go farther and farther and farther and farther, until you reach very high distance, it's gonna reach 0. So we say when the height goes to infinity, this is where the potential energy is 0. Otherwise, it's gonna be negative. This is how they take it's only a question of reference, by the way. And I love this graph because it shows you that you're trying to escape the potential energy. We say escape, and that's why we want it to be negative. Negative means you're bound, you're somehow connected. But when you escape the minus and reach the 0, this is where you're free. You don't feel gravity anymore. Unfortunately, as you're trying to escape, you fall back down in the gravity of the moon. And when you are at this position, you are very close to escape. And this bring me back to this. In this region, you don't feel the gravitational field at all. But if you go to the left, you go into the gravitational field of planet Earth. If you go to the right, you fall back down to the moon, and you cannot escape because you cannot reach potential 0. Okay?
Okay, but what you said, like something negative. What would you mean? Like here on Earth, you said it starts with negative.
So they're gonna take all this potential energy to be negative, and all this potential energy to be negative. And
but why negative?
It's only a question of reference because this is how they do it. It's easier. That's why. It's just this choice. Like for example, when you do mechanics, you take 0 for the x-axis to be the origin of motion, for instance. You can take it to be -100 if you want. When you study fields and when you go into very advanced studies of field, they take 0 at infinity. 0 at infinity means if you are closer to the source, it's going to be more negative and more negative. But the variation is the same. You still gain potential energy as you gain height. Let's say the potential energy at this level, I'm going to change the color. Let's say it's -100 joules. Okay? And as you go up the stairs, it's going to become -50 joules. Tell me, did you gain potential energy or lose potential energy?
Gain, because it's closer to infinity.
Exactly. And when you moved from -100 to +50, how much did you gain? What is delta? 50 joules. If I take another reference, it would be 0 joules up to 50 joules. It's the exact same thing. So what we care about is how much gain in potential energy.
Yeah, the difference.
Reference. And when you go back to topic 2, they take reference 0, the ground. Now in this topic, they take reference 0 to be at infinity. Okay. And they want the field to be negative just to say you're bound, like you fall down into a well, and a well is usually negative. All right, let's go back to the equation. So far, that's gravity. You know, this is the gravitational force, right? The gravitational field is only one component. Don't we know that the gravitational force is m times g? Right, your weight. This is your mass, and this is gravity, and this is it. Okay? So far, we want you and I to try to come up with this equation. How come the potential energy, we know it's mgh. How come mgh is like this? It's not difficult. We're gonna relate it to the force and to the height. And what is v? This is our next slide, okay? So I'm gonna discuss this slide with you. I'm still discussing gravitational potential energy. All right, let me try. I know that the potential energy is mgh, isn't it? mgh, okay? I'm gonna call hr, r the distance away, because you used to call it r as well. When you were discussing the force between two sources, you call the distance r. You did not call it d, you did not call it h. Okay, because r stands like a radius. Mg is the force, isn't it? All right, so I'm gonna call it force times r. And I know force according to the gravitational force of Newton. It's g m source tiny m, which is the test, divided by r squared. And now that you're multiplying by r and r squared are gonna cancel out, and you will end up with this. What is big M? Big M is the big source. Small m is the one inside the field, not the one creating the field. Now, why the minus? It's just to say that I want all the potential energy to be minus. When r goes to infinity, what happens to EP?
Increases.
Let's see.
No, decreases.
To 0.
Yeah, decrease.
So this equation works. I think this is the reason why they took when r goes to infinity, this goes to 0, because the equations would work in a better way. Now that you need the equation of the potential energy, which is not mgh anymore, because g is a variable, that's why you use mgh only when you are very close to the surface of Earth. Now g is a variable. As you go away from the planet, g is actually dependent on r. You cannot use mgh anymore because g is no more 9.81. It's only 9.81 when you are at the surface of planet Earth. What if you are on the surface of Jupiter? What if you are 1 kilometer away from the surface? So that's why I cannot use this anymore. It's only an estimation that could be used at the surface of planet Earth. We're gonna use this. And we're taking 0 at infinity and negative at the surface just to make the equation work. Otherwise, I need to say plus constant. Some people do that, okay? What do they say here? The gravitational potential energy of two bodies is the work done. All right, I don't want to read it. They're saying it's 0 and they're infinitely apart. No, you just ignore it. They're trying to discuss the relationship between potential energy and work, and you know it from topic 2, but I don't want to add to you. This is a mass going close to planet Earth. This is a mass at infinity. So EP here is gonna be 0, okay? And EP here is gonna be negative, just keep that in mind. Okay, and R is the distance. At very far away, you take EP0, this is repetition. This is EP is negative. They take R here to be the radius of the planet because you are at the surface. If you're not at the surface, you need to take radius plus height.
Wait, you said like of its EP equals 0, and where the ball is like on the surface of this planet or whatever. What is it? It's like this equation, right?
Yeah. So you use the equation anywhere you want. So let me write the equation: big M, small m over R. This you can use at any position you want. However, keep in mind that R is the radius of the planet plus the height. Okay. Look. Here, this is small r. I love this diagram. So it's the radius plus how far away. What do we call it? X or height? Usually I call it height because I'm getting higher and higher, farther and farther.
Usually for like small r and big R. That's what we did. Like
yeah, but be careful. Small r is the whole thing from the center to the center. In some books, they call it Z, and Z is the altitude. Anyway, I want you to keep the concept in mind, okay? R is radius because the planet is not point-like. So it's the radius plus the distance from the surface. Probably they're gonna give you R, which is the distance from the center to the center, and you don't need to do anything you want. So we use small r when we're talking about the whole thing. And when you are at the surface, small r is gonna turn into radius.
Okay. So I have a question, like, can we use, so if we use this equation for like the thing above, we can get 0, right?
Yeah,
we will get 0.
Yeah, you replace r by infinity, small r by infinity. So let me write it here. This is where r tends to infinity. So this can be used anywhere, at infinity or at distance big R. Okay. I don't know this slide. I was trying to explain potential, not potential energy. Okay, let me skip it for the moment. Now, what is potential? And this is what I was trying to explain. I had a student called Michael and a student called Joel. And Muhammad and Michael again. Do you need to answer a call?
No, that's the bell.
Okay. So I was saying Joel is funnier than Michael. So Joel has more potential in the funny field than Michael. And then I said the flow of funny jokes would go from Joel to Michael and not the opposite. So it's always, I have the flow from high potential to low potential. And then I said Muhammad is smarter in physics. However, I know it does not exist. Nobody is smarter. And Michael is less smart. So who would help the other? Muhammad will help Michael. So I have a flow from high potential to low potential. And then I drew a mountain. I have A, B, C, D, the points on the mountain. And then I thought if I spill water on the mountain, the flow is gonna happen from C to B and from B to A. So I'm gonna assume that C has higher potential than B and B has higher potential than A. And D and B have the same potential. You can have a tube, Rida, and put water inside the tube. If the tube is horizontal, the water is not gonna flow right and or left. But if you change the potential of the extremities by tilting a certain angle, you're gonna have a flow from high potential to low potential. And then I realized that potential is related to height. But potential is not equal to height. It's equal to height and to gravity. Because if you don't have gravity, you don't have this potential difference. So the idea of potential is something that you never ever discuss very well in your middle school, neither your high school, until you reach electric potential. And I'm sure as a fact that students do not understand what potential is. Potential, يعني it has high potential. In what? You don't understand. Okay? So I think this is the easiest explanation. Potential. Okay? Now looking at the equation of potential, I know what is EP again. Can you remember?
So minus G big M small m over R over R.
Yeah, not squared. And you look at this one. What's this one? Can you give me the relationship gravity? You remember the gravity equation?
The one with the G and M?
Yeah, it's G
M
over R squared.
R squared, yeah.
Okay, how can we relate those two? If I do G times R, okay, let me write it here. If I do G times R, absolute value,
Yeah, you
do I get
cancel
this?
out.
Yes, kid, I need to add a minus. So it's as if I'm saying the potential, didn't we say potential is related to height? And then I said it's related to height and gravity. So it's as if I'm saying mgh. So this is, it's as if I'm saying mgh, and the gh is somehow the potential. This is the potential.
Wait, what is V? Why is it V, VG?
Vg is the potential, gravitational potential.
Okay, but then what's the difference between this and EP?
So EP is potential energy. V is potential without the word energy. And you have all the right to be confused. Because I had this student, every time I asked him to calculate potential energy, he would calculate potential. And when I asked him to calculate potential, he would calculate potential energy. So energy is in joules. If you want energy is in joules, but potential is joules per kilogram.
Yeah, because we have the M.
Exactly. And both of them, they're related to a certain point in space. Let's say you have a planet Earth. And let's say you have Rida. And let's say you have a tiny, tiny child. Tiny child. Rida is more massive than the tiny child. Okay? At this position, Rida has potential energy. At this position, the tiny child has also potential energy. Definitely you have more because it's M related, MGH. So, however, you are at the same potential. How do we calculate the potential? We simply divide by your mass to say how many joules per kilograms.
Wait, you said we have the same potential, but we have different mass.
But different potential energy. So
what?
Yeah, you see, it is confusing. If you're confused, don't forget. Yeah. So
wait, can you repeat?
Yeah, I'm gonna repeat, obviously. So potential energy is MGH.
Yeah, I get that. So
yeah, you have
we don't have the same.
But you have the same GH.
But are we at the same height?
Yeah, let's assume we are at the same height.
Oh.
That I'm gonna call R if you want, or height. So you and the tiny child, your tiny brother, you have the same potential, you feel the same
energy,
but not the same potential energy.
Wait, I thought we have the same potential energy, no?
No, the potential energy is MGH. So it's M related. You have the same.
Okay, yeah.
You are at the same potential, like you feel the same thing, but not in joules. I know it's confusing. Listen, the best way for you to understand this is to give yourself few weeks, few days, you know, to grasp it. So far, you're safe. The equations are there for you. You need to know the equation and you need to know the unit. Now, how to grasp the concept? While you practice, you will try your best not to be confused. And it's gonna come. Probably now with more examples, you will see the difference. Now, if I'm gonna, so this is the equation. Let me change the color, probably red. This is the equation of the potential. So potential, if you want, is related to height and gravity. Potential energy.
Wait, but what about the M?
No relationship with the time. Yeah, it has only relationship with the mass of the source, big M, which is the planet.
Oh, okay. Now I get it. Okay.
Okay, so you saw big M and that's why you were confused.
Yeah, because I felt like it's related to some mass. So.
No, it is related to the planet. So the bigger the planet, the more potential it's gonna create around it. Okay?
Yeah, makes sense, makes sense. Yeah.
All right. So if you want potential and potential energy, they're very similar. Very, very similar. The potential it's not mass dependent. I'm talking about the mass of the tiny bits around the planet. Like you,
Yep.
tiny human, dust, pencils, whatever. This is when you plot gravitational potential. This is megajoules per kilograms.
Gravitational potential is VG, right?
Yeah, you can call it V. Why is it called V? I have no idea. Even in electricity, they call it V, potential.
It's like voltage, we said. No?
Yeah, because it's related to the voltage. Potential, if you do potential difference, you get voltage. In electricity, not in gravity. In gravity,
Yeah, that's what I was doing before.
yeah. In gravity, it's gonna be called G times the difference in height. Anyway. All right, you also have a well. This is three-dimensional. Let's say you are here, Rida. You feel like you can fall down in the potential. Okay.
Wait, what is that's the Earth? Or?
So here you have Earth.
Okay.
And this is the planet Earth. Okay. The potential, if I'm not wrong, inside the planet is constant, but who cares? You will never be inside the planet. At the surface of the planet, you can start with R. So this is negative Gm over big R. And then as you go farther and farther and farther, the relationship is going to decrease to 0, but it's going to be asymptotic. All right? Like, I mean by asymptotic, like if you go to infinity,
Doesn't touch.
it's going to be 0. So if you want EP and V, they behave very similar to each other. Even the graphs are somehow similar. You're multiplying by a constant. But if you need to compare two humans or two objects in the vicinity of the field, this is where there is a difference. Okay? So for the unit, energy is joules. However, potential is joules per kilogram. Okay? If you feel a bit confused, go back to the equations. So far, this is the potential. Zoom out. This is the potential energy. This is the field. This is trying to explain the relationship between G and potential. Forget about it for the moment. It's a bit tricky because it deals with gradient and it deals with the derivatives. Okay? But it is in your booklet, so you should see you should be able to read what's in the booklet. This is my last slide in gravity to show you again the potential well that is very similar to the potential energy well. This is where the planet is, and this is why you fall down to the planet. So this is somehow describing gravitational attraction. I love this one because you deal with this one not in physics only, probably in some topics related to geography. This is a picture of a mountain. These are called equipotential lines. Equipotential lines mean it's a line where all the points like A, B, and C, they have the same potential. And potential for gravity is related to G times H. So which means C, A, and B, they are at the same height. Okay. Have you ever saw a picture like that? It has a name. Like for example, you see the height? This is 1,500. This is 1,000. This is 900. So if you walk on this line, this has an altitude of 900 all the way. If you walk on this line, it has an altitude of 1,000 meters above the sea level.
So if you put like objects on the same line, but like different size, they have the same potential.
Yes, same potential, same height. This is a map for heights. Why am I showing you this? You don't really need it for gravity, but you have the exact same one in electricity. So for you to understand what is the equipotential lines, you need to relate it to this one. This one you use only if you want to go hiking or if you want to create a map that is three-dimensional, and so on. All right, now I'm gonna go back to my outline to show you that we'd finished 1, 2, 3. And again, this is introductory for you. Like the only way for you to feel confident is to sit and do problems. Do I have problems at the end? No. Probably if you want, we can sit for a session to do only problems for this topic. Okay?
Okay.
All right, so now where am I? I'm here. Item 4, electricity and electric fields. All right? You know the electric field equation, K, Q source over distance squared. Remind me a bit what was K?
So 8.99 times 10 to the 9.
Yes. And the unit, you can simply say SI units. All right. What was the unit for E? It's volt per meter or Newton per coulombs. Or you can write volt dot meter to the -1. So this is something you already know. Plus charge, the field is outward. Negative charge, the field is inward. How do you feel now that you know this? You can relate a bit. This is a picture where you have two sources positive. The question is, which source is weaker?
The one on the left.
Yeah, this one is weaker. So the number
less field lines.
Yeah, less field lines. And here both are negative. So you see it's the same diagram, but this one is outward, this one is inward. And since they are similar, you have this weird shape. By the way, this is not E1 and E2 as an electric field. This is E total. And by E total,
What do you mean?
all right, like let me show you here. I have source 1, right? I'm gonna call it source 1. And I am gonna call this source 2. Okay, at point P, I would feel E1 and E2. So P will not feel E1, will not feel E2. P is gonna feel the resultant of E1 and E2. And you know, you know how to find the resultant of two vectors. It's a bit tricky, but you know what I'm talking about.
Yeah, like the vectors thing.
Yeah, I know it's crazy. Here, it's good to discuss a bit. You have a positive source, so E1 is away. You have a negative source, so E2 is towards it. That's why you have E1 and E2 pointing this way.
Wait, P is positive or negative?
Here, one is
positive.
Yeah, it shows because it's Q, and this one is negative to Q.
So P is positive.
P is a point. No, P is a point in space. It's not a charge. It's a mathematical point. So remember, the field is everywhere, even if you don't have charges. Like here, you see this.
Wait, but we said the electric field is like a region in space. So when a charge has a force because it has a charge or whatever. So
yes,
if you have a field, you should have a charge, no?
All right. So you need a source of charge.
Yeah, like you need a charge, no, to have electric field.
Yeah, this is the source, and this is what it creates. This is another source, and this is what it creates. Here you have nothing. But you cannot feel it unless you have something. Let me explain. Gravity. Do I have gravity at this point? Where the tip of my finger?
Yes. No.
But how do you know? How do you know? It's nothing. There's nothing here. Who is the source?
What do you mean?
Who is the source of gravity that is here at this point? Who creates the field?
Your finger. No, that's the hand.
Planet Earth, right?
What?
Okay. So in this region between my face and the screen of my laptop, there is gravity. Who creates this gravity? Planet Earth. So planet Earth is the source of the gravity, but I cannot see it. I cannot smell it. How can I make sure there is a field in here? I grab a pencil and I let it go. It will fall. So I know for sure there is gravity in this region. Okay?
Yeah.
So gravity exists even if the pencil is not here.
Okay, yeah.
Who creates gravity? In this region, it's planet Earth. Okay? Yeah. So let me try to remove a bit of those. All right, so what I'm trying to say here, I'm trying to say that this is one planet if you want. It will create this field. This is another planet if you want, or however it's a source of, it creates this field. And at P, I have nothing yet. So I find E1 plus E2, I find the resultant. If I get a tiny electron and put it here, it will feel the field. But the field is there even if there's no test charge.
Okay.
Okay. All right. Like here again, this is also interesting to see, plus minus. And let me remove those because I'm gonna discuss them later. Okay. Plus and minus, what you can see here is not E1 created by 1 and E2 created by 2. It's the total. It's out of the plus into the minus, and around the minus you have more field lines because apparently it's stronger in magnitude. And here it's very similar, okay? So this is what is electric field. So we know how to draw it and we know how to calculate it, period. Now, electric potential energy. I need to remind you that that was the equation of the field, gravitational field. And that was the equation of the potential energy of gravity without the minus. I'm taking it absolute value. Can you tell me the difference?
So we said we need to multiply, like the second one is with respect to two like objects or two masses.
Yeah.
And
here I have an extra m, and here I have an extra squared, right?
Yeah.
Remind me, what was the electric field equation? It's K.
The K Q1
over R squared, right? What's the force again? Remind me, what was the electric force? K, Q1?
Q1, Q2.
Over distance.
Over.
Okay, so this is the force, and this is the field. The field, you take only the source, only one Q.
Yeah. So it's the same, like you put it in.
Yeah. By the way, all my students, when I ask for force, they find the field. When I ask for field, they find the force. So they confuse those two. So force is in newtons, field is like gravity, but it's an electric field. This is in newtons, this is in newtons per coulombs, okay? Now,
yeah, I know.
Yeah, so now the difference between gravity, like field and energy, add a mass and remove the squared. So what I did here, I took the same equation, I added another tiny q, and I removed the squared. I did the exact same thing. What is electrical energy? It's very similar to potential energy, gravity. If I take the pen and move it away from Earth and release it, what happens?
It will fall.
It will fall down. Now, if I take a plus and get it closer and closer and closer and closer to another plus and release it, what happens?
It will repel.
It's gonna fly off, exactly like potential energy. So potential energy is energy stored. Gravity gives you potential energy. As you go away from Earth, you release, it will fall back down. If you have an elastic band, you stretch, it will store potential energy. You release, it will fly. Here for electricity, repulsion and attraction will help you store a certain energy called potential energy. Okay, so plus.
Wait, so is electric? Oh, sorry. Is the electric potential energy related to the gravitational potential energy, or not really? You're just comparing them.
They act the same way. They're not related because you need gravity for gravitational potential energy. You need electricity like charges. They are two different universes. They're not affected.
Okay, yeah. So in an exercise, I won't need to use like both together.
No, but I'm showing you both to make sense how I moved from this. They have the same behavior, that's all. When the session finishes, let's say you grasp 50% of the concept. It's okay, Rida. All my students, nobody would go to understand 100% of the concept. You need to know that topic 10 is the hardest in your book because it deals with fields. You know, field theory is something very advanced. Okay? At the end of the day, you need to know the equations well and you know how to solve the problems. And trust me, the problems are typical. Like you would have questions, these types, and you know how to solve them. Don't be scared, okay? Okay. I have a tiny chance to help you with understanding the concept. If you can understand 50% of it, it's great. Okay? You will study this again probably at uni. All right, now potential, exactly what I did with the other potential. I remove a Q, that's it. In the gravity, we removed an M. And what is the difference?
You want me to square it, no?
All right, let me show you again the difference between potential and potential energy. It was here. So this is potential and this is potential energy. This one has an extra M.
Oh, yeah.
Okay. If you want the unit would help you. The energy is joules. The potential is joules per kilogram. Now here, the energy is joules. The potential is joules per coulombs. Because you removed the
okay. Here it's no longer negative, right?
Yes, they don't deal with negative because the negative is inside the Q. If you have a negative Q, the potential is going to be negative. So now Q will dictate which means so far for force and field, we tell you to put absolute value for the Q. But energy and potential use the minus because minus means you are attracted, you are bound in a way. Okay. All right. So how do we find potential? You see, potential is energy divided by Q, or energy is potential times Q. You can use both equations and no need for the minus. Let me check the equations in the booklet. Do they put minus? So this is the potential. It has no minus. This is the potential energy. It has no minus. And the force, you know it. They did not write the field. Field and force are the same. Just remove a Q. All right, now back to our slide, which was here.
Wait, E equals QV. Where did this come from?
Yeah, this one. Didn't we say energy? This is in joules, and this is joules per coulombs. It's as if we're saying that potential is energy divided by charge.
Oh, so we replace V by the first equation. Okay.
Yeah, exactly. Okay. All right.
Yeah, makes sense.
Did we use it here? Yes, we used it here. So didn't we say that V is GH? So this is MGH.
Yeah, okay.
You have to say GH because G is not 9.8. It's a variable as you go away, but you can say V is GH for gravity. Okay?
Okay.
Yeah, summarize the equations and solve problems. You will be okay. After we explain what potential is, this is a point A, this is a point B. They have a potential difference because A is far from the source and B is farther from the source. So different potential because the potential is R dependent. So if you get a voltmeter and measure the voltage between A and B, the voltage is gonna be the difference in potential. Okay, so the unit for this guy should be joules per coulombs or simply volts.
Yeah.
Okay, so volts, is a derived unit. All right, here they're trying to explain the potential. This is a big source of radius R. It's very similar to this is a positive source because you know, back in gravity, it was a negative potential. Now I have a positive potential because it's a positive source. And you see the behavior is very similar. It's KQ over R. That's why it's a downward behavior because you're dividing by R. Inside the charge, if you go inside, the potential is constant. Okay, this is something new to you. Don't worry about it, just a fact. This is where the source is negative. So A is for a positively charged sphere. Let me zoom in. You don't need to. Yeah, and B is for a negatively charged. So yes, there's no minus in the equation because the minus is inside the Q. If Q is positive, the equation is gonna be positive. If Q is negative, the equation is gonna behave like a negative function, which means you cannot take Q to be absolute value. The minus is very important in here. Okay, this is a three-dimensional picture. This is a negative source, and this is so pretty, and this is a positive source, and this is a mapping of the potential. I love it. I love to see it. I don't know why. Now, equipotential lines. This is the equation for potential for electricity, and this is the equation for potential for gravity. Do you see how they're similar? K and gravitational constant. Q source, mass source, distance, distance. This one has a minus. The electricity, the minus is either inside the Q or not existent.
Yeah.
This is a planet. And you know, each point, like if I take point D and point C, D has a height, C has a bigger height. However, C and B have the same height because they are at the same circle, the same radius. So ABC, same potential because same R. So the line ABC is an equipotential line. Equipotential line is a line of the same potential.
Okay.
For electricity, it's the same thing. If I have a plus, the equipotential lines are those. So let me show you. An equipotential line is the black line. And the blue is the electric field. And this is not positive. It has to be negative because it's inward. So I'm going to remove this, do this, and put a minus sign. Okay? I want you to notice that equipotential lines and field lines are always perpendicular by definition because they're opposite. If you go along the field line, the potential increases or decreases depending if we're talking gravity or electricity. So by definition, they should be perpendicular, which means if you know how if you know how to draw the electric field lines, you can simply draw any line perpendicular to them to be able to know the equipotential line. So this isn't it perpendicular? The green is perpendicular to the black. So this is an equipotential line. Here, equipotential. Here, this is an equipotential line. And then it's gonna curve. It's gonna curve. All these points have the same potential. It's tough to draw.
Not the same potential energy necessarily.
Not necessarily. The same charge, yes, they have the same potential energy. So multiply by Q to discuss the potential energy. So far, I have no charges. It's an empty space. I'm just saying this point would feel a certain potential. Okay, so it's hard to see the equipotential line if we have two sources. I have good news. Potential and potential energy, they are scalars, so you can add them up. This is very good news. Let me explain why. Probably by showing you this nasty picture. You see here, I have to draw E1, I have to draw E2, and I need to struggle to find E total because we're talking about vectors. F is a vector and E is a vector. However, E as an electric field, EP as an energy, and V as a potential, both they're scalars. Like you can find the potential created by one, potential created by two, and add them up. Well, that's it. This is really nice. When you do problems, you're gonna be thrilled. You're gonna say, oof, that's it.
Wait, but if you add them, what does it mean?
You can find, okay, like here, it's so tough. Let's say I ask you to find the potential. Let me grab a red pen. I ask you to find the potential at this point. You need to find V1 created by 1, find V2 created by 2, and then how do you find V total? Simply add.
You add them. Oh, okay.
Yeah, one will be positive.
Why did you write EP and then V, not like V and V? That's why I was confused.
Yeah, so EP is the energy. So back to this. I want an equation where I have energy and potential. Here, okay. This is EP and this is V. They're both scalars. So if you want the energy at a certain point, you find energy created by source 1, energy created by source 2, and you do plus, you add them. One of them would be positive probably, one of them would be negative probably. Take the plus and minus into account. You will end up probably with a negative source, with a zero answer if they're equal and opposite. Okay? I know for a fact that this is a lot for you to handle. I'm gonna save it. I'm gonna send it to you with the edits. Let me know if my pen does not show. In the remaining time, I hope you're not busy the last 5 minutes. Are you busy? You have class or something?
No, it's okay.
We can stay for 5 minutes just to give you the time that we lost. Not this book. This book. Let me show you some solved problems and probably send them to you. Do you have this book?
Yeah, I have it here.
Okay. Yeah, if you have this book, the presentation is mostly taken from it. It's a summary from it. What you can do, Rida, try to read those and see how easy they are. Calculate the difference in the potential energy of a satellite of a certain mass when it's taken from the surface of Earth to a distance. So you find potential energy at 0 distance, then you add the distance, and then you do the minus, the difference. Trust me, if you don't do a quick practice, you will forget everything we discussed today. Here, calculate the potential, just potential. So you find potential from 1, potential from 2, you add them, very easy. And you have all the equations. Here, what do they want? You have point P, and probably you need to find something from source 1, something from source 2. However, you don't have X, you need to solve for X. Probably they want to know at which point those something would cancel out. So you need to say gravity and gravity, make them equal. Okay, so you would say that the two fields are equal and opposite because it's 0 at this point. To solve this equation, my students did quadratic equation. It was a bad idea. The best idea was to square root both sides and to solve. It's much faster. Okay, probably you don't know what I'm talking about. The best way is for you to take some time to read it. D is the distance, X is unknown, and you take this to be D minus X, or otherwise you need to take X and Y, and X and Y should add up to D. Try it, okay?
Yeah, makes sense. Yeah.
Okay, this is a question related, probably you need some graph skills. They ask you, for example, at this height, what would be the potential? You do the calculation. Work is something we did not discuss, but the work is equal to the change in potential energy. So you can simply say work is the change in potential energy. Like in mechanics, don't you say the work is the change in kinetic energy?
Yeah.
And you know, if the kinetic energy increases, the potential energy decreases. So the change in kinetic energy and the change in potential energy are equal and opposite. Okay? Think about it.
So if potential energy increases, kinetic energy increases.
Decreases.
So how?
All right.
Why is it opposite?
All right. A pen free falling. What happens to potential energy?
Oh yeah, makes sense. Because when it decreases, like it's moving, so it makes sense.
Yeah. So the change is equal. Like you lose 20 joules, you gain 20 joules. So the change is the same, but one is positive, one is negative. All right, Rida. So before you go, topic 5. Okay, this is our plan. I'm gonna keep it. I'm gonna call it plan for Rida and keep it and update it. Plan for Rida. All right, you can add to it. I'm gonna say that studying alone. I heard you have a question. Rida has questions. Probably they were urgent.
1 and 10.2, that's it? Or is there more to it?
This is only 10.1. So for 10.1, yeah, 10.2 could be a bit easier because it's an application. We did a quick summary. This is what we did. Okay. Rida must do the blue problems alone. Okay. I mean by blue problems, those. I call them problems. Okay. Rida must later on do extra problems. So the blue problems for me is only to get started, but they're not enough. Topic 10.2, if you like the idea, you can give me feedback later. I can give you a quick summary. Probably the quick summary was overwhelming for you. Think about it.
No, it was okay.
A quick summary, probably it's gonna get you started. I don't know. Okay? Probably you will tell me, Miss, I'm gonna read it alone in the book. You do problems with me. Or probably...
Yeah, I'll see now what I'm doing.
Okay, and then we have blue problems that I have, you decide, and then extra problems. By the way, for me, I would follow the same with topic 5. If I were you, I do quick summary alone on a paper, blue problems alone, and then extra problems given to you. Okay? Topic 11, I believe your teacher started it. I don't know how much you're understanding in class. Probably you're doing okay, probably half okay. Okay?
Yeah, like for now, it's okay.
Yeah, for me, I would say quick summary, blue problems, extra problems, also for topic 11. Okay, extra problems, where do you get them from? It's either the yellow problems in your books, if you have answers, or I give you from my IB question bank. Tell me when you want extra, okay? But I don't want to overwhelm you. I'm gonna stop recording. I should have done it before.